In this section, we'll be using our trigonometric functions to solve applications, problems, and models involving right triangle scenarios. Here we have a right triangle. If we label our angle with the uppercase letter A, B, and C, the sides across from our angles would be lowercase a, b, and C would be where our right angle is. If we're given two sides in a scenario, we can always use the Pythagorean theorem to find the third side. If we're given two sides, we can always use our trig function to find angles such as theta here. So if we're given side A and C, we know theta is equal to the arc sine of A over C. If we're given B and C, we could find theta by using the arc cosine of B over C. And if we're given A and B, then we can use theta is equal to the arctan of A over B. Now let's look at an example. So here we're given that side B is equal to 16 units. Side C, the hypotenuse, is equal to 52 units. So we're trying to find side A, and angle B. Since we're given two sides, we can use our Pythagorean theorem to find side A. We know side A is equal to the square root of the hypotenuse squared minus B squared. And this comes out to give us 49.48 units. Now that we know all three sides, we can proceed to find our angles A and B. We know angle A is equal to the cos inverse of 16 over 52. And we're using cos inverse since we already have the adjacent side and the hypotenuse. So A is equal to the cosine inverse of 16 over 52, which on your calculator would be second cosine of 16 divided by 52, and this will give us an angle of 72.08 to 2 decimal places. To find angle B, we could use our trig functions again, but it would be simpler since we know that within a triangle, all three angles add up to be 180 degrees. So if we subtract angle A and angle C, which is 90 degrees, we can find angle C. So it's 180 minus angle A, which is 72.08, minus angle C, which is 90 degrees, give us angle B, which is 17.92 degrees. In this example, we're going to find the altitude of an isosceles triangle. An isosceles triangle is one in which two sides are equal or two angles are equal. Now this isosceles triangle is not a right triangle, but we can make it into a right triangle by dividing it into two equal halves. So if we draw a line straight down, this line here becomes our altitude, which is what we're trying to find, and it divides the base evenly. So this side would be 5 and this side would be 5. Since we have an angle and we have a one side of our right triangle now, because here we have a right triangle, we can use our trig function to find the altitude. We could use our tan function. We know tan is equal to opposite over adjacent. So if we say the tan of 18 degrees is equal to the opposite over adjacent, we know the opposite side here is our altitude, and we know the adjacent is 5. By multiplying both sides by 5, we get the altitude is equal to 5 times tan 18. Plugging this into our calculator, we get the altitude being 1.62 units. In this application, we're asked to find the height from the top of a ladder to the ground. So here we're trying to find this distance from the top of the ladder. So here we have our ladder. And the ladder is 20 feet and it leans against the side of this building. So here we have our ladder 20 feet. They're telling us also that the angle of elevation, so we're looking up, this our angle of elevation is 80 degrees. We know from our sine function that sine of theta is equal to the opposite over the hypotenuse, and since we're trying to find the height here, we should use a sine function. So we're told, so that we know that the sine of 80 would be equal to the opposite, which is a height, over the hypotenuse, which would be 20 feet. If we multiply both sides by 20, we get 20 sine 80 is equal to our opposite side. Plugging this into our calculator, we get 19.7 feet. 20 sine 80 is equal to 19.7. So the height of the ladder above the ground would be 19.7 feet. In this example, we're told that an airplane is flying at 600 miles per hour and has a bearing of 52 degrees. After flying for 1.5 hours, we're trying to find out how far north and how far east would the plane have traveled from its point of departure. So here we're assuming this is our point of departure. Our bearing is 52 degrees. We know for airplanes, the bearing is measured from north. So here, this is our bearing of 52 degrees. 600 miles per hour at 1.5 hours, so this 1.5 times 600 will make our distance equal to 900 miles. Now if we construct a right triangle here, this distance here will give our northern distance, and this distance here will be our eastern distance. We already have our hypotenuse, which is 900 miles. We know from our trig function that the sine of this angle, which would be 38 degrees, since this is 90 degrees, so the sine of 38 would be the opposite, or the distance north over the hypotenuse, which is 900. So if we multiply both sides by 900, we get opposite, which is our north, is equal to 900 times sine 38. And 900 times the sine of 38 degrees would be 554.1 miles. So the plane has actually traveled 554.1 miles north. By taking the cosine of 38, we have the adjacent over the hypotenuse. Once again, multiplying both sides by 900, we have the adjacent, which is our easterly distance, equal to 900 times the cosine of 38. 900 times the cosine of 38 comes out to be 709.2 miles. So the plane has traveled 709.2 miles in our easterly direction. Here we're told that our ship is 45 miles east and 35 miles south of port. So here's our ship down here, and here's our port. So it's 45 miles east and 30 miles south of port. The captain wants to sail directly to port, so we're going from here to here. So the captain wants to sail directly to port. What bearing should be taken? So here we have our vertical distance, or the opposite of this angle theta, as being 30. Our adjacent side would be 45. We know from our trig function, since we have the opposite and adjacent, we can use our tan function. We know tan of theta is equal to 30 over 45. So theta is equal to the arctan, or tan inverse, of 30 over 45, which comes out to be 36.7 degrees. Now, so tan theta here is equal to 36.7 degrees. We're trying to find the bearing of the ship to the port. So if we draw our vertical axis here, this is now our north, so our east, south, and west. When we find the bearing of a ship, it's measured from the north. So if it's in this quadrant, it's also from the north. If it's in the southeast, it's also from the north. If it's in the southwest, it's also from the north. So here, if we subtract 36.7 from 90 degrees, since this entire quadrant is 90, we get 53.3 degrees. So our bearing would be 53.3 degrees. Not only do we write it as 53.3 degrees, we need to specify which quadrant it's in. Since it's in the northwest quadrant, we write north 53.3 west. So here's our bearing of our ship, north 53.3 degrees. If it was in this quadrant, it would be north 53.3 east. If it was in this quadrant, it would be south 53.3 east. And if it was in this quadrant, it would be south 53.3 west. So for ship bearing, it's always north and east north with the degree from the north in between.